Well, thank you very much for inviting me, and I'm happy to be your first speaker. And the timing turned out to be perfect because we have a very odd result that will come out, we believe, in the next month or so in Nature. And so that's what I'm mostly going to get to, but I have to tell you a lot of context before I explain that. And so I'm guessing that most of the people here are astronomy or astronomy adjacent people. I know that there are a lot of theorists, and so I'm going to try to explain some of the observational techniques a little bit more than I might if I was talking to only observers. But if I make no sense or if I don't say enough about theory, please do go ahead and interrupt me. Okay. And there's a long list of people who have been intimately involved in the work that I'm going to show you, longer even than the list that's on the screen. But the most important person on that list is a very brilliant graduate student at Harvard, whose name is Catherine Zucker, who works with Doug Finkbeiner and with me on her PhD thesis, and who this year worked with also João Alves, who is actually the first author of the paper that I will talk about in a little while. And so just to show you what is in that paper, so this is the figure that you can't show anybody. Okay? And I'm going to explain this to you and show it to you in 3D and tell you where it came from and all kinds of good things in a little while. But just so you know, if you want the punchline first, this panel here is a top-down view of the galaxy. What you see in grayscale is a map of the dust in the galaxy in 3D made from a statistical analysis of the colors of stars using pan-stars data and also distances from Gaia data. And so I'll explain all of that later. But what you see is highlighted in red here is a long chain of what we would formally call molecular clouds. These are famous things that have names, like Orion and North American Nebula, et cetera, but they all have names. Okay? From the top, this makes a very straight line, which is very strange. From the end, it's pretty compact. This is several tens of parsecs across. That's sort of end on. And then this is the weirdest one. From the side, it makes a damped sine wave with an amplitude of about 150 parsecs and a wavelength of about 2 kiloparsecs. And you might think this is some weird feature of the local arm. Turns out it is the local arm. Okay? And the sun is actually off from it over here, this picture. Okay? Again, I'll show this to you in 3D and play with it, and I'll give you a secret link if you ask me nicely. But this is kind of the end of the story that I'm going to tell you, is that there's this bizarre, unknown, before now, structure in the local Milky Way. But for those of you who are not great aficionados of the Milky Way already, here is a pretty terrible cartoon that I tried to assemble for you just to tell you what all the jargon is about different parts of the Milky Way. And so there's a disk of the Milky Way. Actually, there's a thin disk and a thick disk, and how thin and how thick you can have a whole discussion about. So we'll just say there's a thin one, there's a thick one. There's a bulge, how big this sort of spherical bulge is, unknown. There's a halo that has more to do with cosmology and the formation of the Milky Way. We thought, I'll tell you more about that in a minute, than other parts of this. There's a bar here in asymmetry in the middle of the galaxy. There are the famous spiral arms, although what we're going to think about today is just how neat they are or aren't. And then at the edge of the disk, there's some sort of flaring. And so there's hundreds of papers about each one of those things. But if you want to look at this historically, you can say that people like Aristotle are responsible for views of a spherical and infinite universe. Okay, so we've preserved some spheres, and then many people. That music that you heard at the beginning was from William Herschel, who also was an astronomer, and many people give him credit for the idea that there's a disk-like distribution of stars that explains the stripe-like distribution on the sky for the Milky Way. Thomas Wright actually predated him and thought that there was an infinite disk-like distribution of stars. And then some guy named David Spergel really cemented the idea that there is a bar in the Milky Way with Leo Blitz using infrared data 25 plus years ago. Other people suggested that before, so if David were here, I could tell him I did this just for him. But anyway, so there's a bar in our galaxy, and then there are spiral arms. How many spiral arms and what they look like is currently definitely still at issue. But here's just one cartoon, again from work by David Fergal. And if you notice, I thought that was really interesting. This little teeny, oops, wait, let me go backwards. Sorry. This is the wonderful Institute for Advanced Study laser pointer that I was given. And there's apparently some sort of IQ test where you have to remember to push the button in the middle to advance the slides. And this button is the laser pointer. But what I wanted to show you is this teeny tiny dot is the sun. And in this model, it's shown with its own little sort of Orion spur, not knowing what that is. And interestingly enough, there's this long straight thing over here that was already predicted in the analysis of the infrared data. And again, when David comes back, someone asked him if he ever noticed that that was unusual. Okay, so you're probably familiar with this diagram, which is just Hubble's arrangement of galaxies into types into this famous tuning fork. And now, if you look at something like a giant survey of many galaxies from, say, Spectra, you can see tons and tons of examples of all different kinds of galaxies. And the issue is that we have great views of the structure of galaxies that are not our own. But of course, we all know that we are embedded in the disk of our galaxy, and so we have nothing like a real view of our galaxy that looks like this. That's extremely unfortunate. And pretty much what the work of Catherine Zucker is about for her thesis is putting together observations of the gas that are kinematically resolved, observations of the dust that's mixed with the gas where you can measure distances, and observations of the stars to try to knit together a picture of the Milky Way. Okay? The picture will have higher resolution in some ways than this, but not in useful ways that give us a top-down view. So that's unfortunate. Okay? But if we pick one of these galaxies that's a sort of spiral-like galaxy and zoom in on it, this is actually Mark Reed, who, for those of you who don't know, is one of the world's experts on the structure of the Milky Way from observing masers with VLBI, which is a technique that gives you very accurate distances and makes it possible to make models of the structure of the galaxy, which again, I'll show you later. But anyway, this is Mark's personal favorite Milky Way analog galaxy. And if you look at it carefully, you'll notice that there are these long, straight parts. It has a bar, and it has various stretches that, if you look carefully, this is not a spiral in the sense of it's a perfectly log normal curved thing. Okay, there are these weird long straight bits, and if you try to figure out, like, if you theorist or observer, okay, if you just looked at this, how many arms does this galaxy have? I don't know. I could do that just to help you. I can sort of draw two arms on there, but what about all that other stuff? And should I draw the arms in dust, or should I draw them in stars? Or, and there's actual disagreement amongst people who do know what they're doing in terms of determining how many arms. And by the way, I'm not including me. Okay, so my background is mostly in studying star formation, and I got some interstellar medium and dust. Where's Bruce? Dust work. Anyway, but I got into this because it became possible to do things with the same sorts of probes that I used to use to study local clouds, to study the galaxy. So if I say things that seem uneducated about the structure of the Milky Way, please correct me. I'm trying to learn. Okay, so anyway, but bigger experts than I will tell you that there is disagreement even in the Milky Way about how many arms it actually has. And importantly, I'll show you some numerical simulations in a minute about sort of how good those arms are in terms of whether there's a lot of structure in between them. If Eve were here, we would talk more about the spurs and feathers that she's been working on and discovered long ago. But it turns out there's structure that aren't even just like these feathers off of the spiral arm, but all kinds of webby structure between the arms in numerical simulations. And observationally, it's really hard when you're in the disk of something like that to tell the difference between something that's in an arm and sort of tilted or between an arm. And even if there are arms in some cases. But just for reference, the diameter of that galaxy is about 40 kiloparsecs, so not too different from the Milky Way. Okay, so I showed you this picture, and I explained it just a little bit, but I want to point out that the scale bar here, so that's 500 parsecs. Okay, so it's like almost a kiloparsec. No, that shouldn't say 500 parsecs. Oh, 500 parsecs, right, sorry, that's correct. Not a kiloparsec, this is almost 3 kiloparsecs across that box. Okay. So I promised I would explain where this all came from and what the techniques are that let you do this and how the statistical approach works at the end. So this is kind of a map of the whole talk I would love to present to you today. So the data come from spectral line mapping, so mostly radio observations of large bits of gas. And then also, I've listed numerical simulation under data, because the way in which we're using numerical simulation is to make synthetic observations of them. So we're considering them data in our analysis. Not necessarily fully reliable data, but data. Okay. And then standard imaging, very deep imaging, and imaging over time, like what happens with Gaia, is also critical. And then the most critical piece for the Radcliffe Wave, by the way, it's called the Radcliffe Wave, even though nature doesn't really want us to call the Radcliffe Wave, because João Alves, who I mentioned as the lead author, was a Radcliffe Fellow. So we too have an Institute for Advanced Study. And one of our fellows this year, who was there all year, is João Alves, who's normally in Vienna. And he came to really appreciate both the environment that Radcliffe gave him to do this work, and also the history of the computers and astronomy tradition at Radcliffe. And so he wanted to name it after Radcliffe. And Leslie Sage is still deciding whether or not we can do that. So it's the Radcliffe Wave. Okay. So anyway, right. So the statistical reconstruction that lets you get all these distances is the part that's really, really critical. So if you look at gas and you make 3D visualizations of what's called position-position velocity space that we'll talk about again in a minute, you can make beautiful movies like this. But the problem is that happens to be the Perseus molecular cloud. That, we thought, is not necessarily representative of real 3D space. Okay? There's no Hubble flow in molecular clouds. You can't just take velocity and turn it into distance. But you can see that things that are at different velocities are probably at different distances. This is actually the newest version. It's a sort of weird coordinated version, but it's showing you the galaxy from the bottom there and then from the top in the original view locally at a scale of a few kiloparsecs out to the edge of that from Greg Green's latest analysis of this 3D dust data that I promise I'll explain at the end. But that basically is what's in the background of the Radcliffe Wave image that I showed you a minute ago. Yeah, Jim. Exactly. So I mentioned that we have higher resolution in some ways in our galaxy, but lower resolution in others. And the low resolution is along the line of sight. So the sun is there, and then the distance bins. How long those are depend on the number of stars that you can observe, and you trade off uncertainty for resolution.
On the left-hand
yeah.
panel, I don't see radio uncertainty.
Oh, that one is just a volume visualization, but actually the uncertainty in that is extremely small, because that's actually from that's not real distance. That's radial velocity from spectral line observations, where the velocity uncertainty is tiny, tiny compared to what you can see there. So that's not a problem. But over here, this is a big problem. But what's important is, I don't know if you can see it from where you're sitting. It's a little hard to see because of the way that this is done. But this big, long structure here is what the Radcliffe Wave is. And importantly, it's not along a line of sight. So that's good. OK, so another result that has constrained the structure of the galaxy recently in weird ways that came from our group was this thing over here. That again, I promise you, I will explain the details of all of these things. Let's just give you a map of where we're going. And what we found were some very unusual, very long and skinny, dense molecular clouds that lie in the disk of the galaxy. And when I say long and skinny, I mean like 300 parsecs long and 1 parsec wide. Okay. So the other thing, the Radcliffe Wave, this is longer. Oops, sorry. I really have to use my own pointer next time, but I can do it this way. So the Radcliffe Wave is like 2 kiloparsecs long. So Nessie, the other thing, the bone that I showed you a minute ago, would be only about that long, 300 parsecs. But this is along its end, say 50 or 60 parsecs wide. But these other things are like threads. They're like 1 parsec wide, okay? And they lie exactly in the plane in the inner galaxy, okay?
And that's the only molecular gas in that square?
Everything that you see in the grayscale is the only molecular gas in that square. Yeah.
And the grayscale is the dust.
Sorry. Yes, I'm assuming that the gas and the dust are mixed together. So we don't know the distances to the gas as well as we know the distances to the dust. But I'm going to show you how we connect them at the end. Sorry.
So which objects did you choose to highlight in red?
What's done? I have a whole thing where this is all bigger and zoomed in, so I'll answer you quickly now, but then I'll show you in more detail later. But the answer is basically there's a rectangular prism sort of put down through here, and then there's a statistical fit to a sine wave, a damped sine wave, and the things that are highlighted in red are the things that are constrained by that fit to be in that structure. But you could argue that there are other things too, and I'll show it to you in 3D, and you can choose your own structures in a minute. Okay. Oh, sorry. This is the danger of, okay, where are we? Sorry. Okay, so that's where we were supposed to be. And then, wait, I'm sorry. Too far off course. Right, that's where we were supposed to be. And then what I wanted to show you again was the techniques, okay? So there's the spectral line mapping, the simulation, the imaging, the statistics, and then you get to these things. And what I wanted to talk about was the techniques, kind of one at a time. So before I do that, though, I should just mention that the origin of this thing, this Radcliffe Wave, is still at issue. And we can talk about various processes that are listed at the bottom there later as possibilities. OK, so to explain the techniques a little bit more, here's just a cartoon of a little section of the Perseus molecular cloud, the one you saw in 3D a minute ago. And this is very much not to scale. There would be thousands and thousands of spectra in a spectral line map like this, OK? But what happens is you take a radio telescope and either use an array or use interferometry or you point your telescope a lot of times. But however you do it, you get a lot of spectra on the sky, and you wind up with these grids of spectra. And what people very often do is they just integrate under each spectrum and say how much gas is there of whatever that tracer is, and I don't care about the velocity distribution. And if they do that, they just plot something that looks like a contour map. And if you're talking about a mountain range, you know, unless it's like an earthquake, the mountain range doesn't move very much, and that's a fine representation of all the data. But we actually have all of these line shapes, and we know the velocity distribution. So you don't want to do that, okay? You want to actually try to use the velocity data. So this is an old project, but this is where the Perseus example came from, and we'll return to it later. So let me just show you that this is an ancient image from Barnard from the 1920s in the background, so just an optical image. And that what you see there is lots of Spitzer data and lots of stuff about young stars that we don't care about today. But what you care about is that if you take those green contours and instead of adding everything up, you actually use the velocity information, you can make this three-dimensional picture of Perseus, except that the depth dimension is just the velocity. Okay? It's just the x-axis of those spectra. It's not actual distance. So but it sort of is. We'll come back to that.
So line CO, which line?
This happens to be 13 CO, yes. Okay. So, and actually here's the list of everything that's on there, just in case you want to know. So that is, in fact, 13 CO. And I'll just leave that there for the star formation aficionados for a minute. Okay. So again, we wish that we could do what we can do with the numerical simulations and have 3 dimensions of space and 3 dimensions of velocity that we could measure all at the same time, right? But we can't do that. And with spectral lines, what we can measure is the plane of the sky, so x and y, and then just the Doppler velocity, just the z component of velocity. So that was what you were seeing as 3 dimensions there. And so that's called PPV space, or position velocity space. And so in the radio astronomy world, that's sort of been the 3D world for a very long time. Okay? So that's the spectra. Now, in terms of numerical simulations, it is possible to make 3D position velocity maps. But it's much more computationally expensive and fraught to try to calculate synthetic spectral lines from these maps. So often what happens is people just do this, and this is just PP now, not PPV. Okay, and these purple contours on this model from Rowan Smith and collaborators of a Milky Way-like galaxy, the purple shading is where you would see CO emission. But it's not been calculated what you would see if you were at the sun's position and looked out this way, what you would see in terms of a spectral line profile. This is just what are the temperature and density conditions, would you get CO emission at all? And so this particular paper is actually about CO dark gas. And so all this gray stuff, I'm sorry for anybody who's colorblind, but the stuff between the arms mostly doesn't emit in CO, okay? So that's interesting on its own. So back to Jim's question, you know, these things here, you might be able to see them in dust when you wouldn't be able to see them in CO. So that's a confusion that's hard to get around. But anyway, so a lot of the work on simulating galaxies, the resolution is way, way too coarse to be able to see anything like either of the kinds of features that I'm talking about today. So when you look at those gorgeous pictures of external galaxies, you know, the resolution on an arm is like this big, okay? You can never see this, not never, but not yet, okay, see these fine, fine scale structures. So that's why we are interested in the Milky Way. Okay, so now to get to the first of the sort of oddities is these bones. And so if you just look at imaging, so this is a Spitzer image in the background. It's a little hard to see it on that image. So I'm going to take off the dots in just a second. But just so you know, these two lines, but what you can't see behind the dots and what you'll be able to see when I click to the next slide is a very long dark line, okay, on this, which is a so-called infrared dark cloud. Okay, so this is a cloud that's dense enough that it absorbs the mid-infrared just from the dust in the cloud, the mid-infrared background. The scale of this image is on the next slide, and I'll show you, but this is 300 parsecs from here to here. Okay, and what I was about to say is that the two lines here show plus and minus 20 parsecs from the galactic plane. Okay, so when I say this thing is in the galactic plane, I actually mean it's in the galactic plane. Okay? And what we wrote about is that we believe that if you have a cloud that's 1 parsec wide and 300 parsecs long, it's not going to last very long, and it's not going to form randomly. So we actually think that they mark the gravitational midplane, at least locally, of the galactic plane. And so we've set out on a search for many more of these, and I'll show you the results in just a second. But what I wanted to show you here is that these colored dots and the colored lines are showing you the predictions from galactic rotation of what the velocity of the gas associated with that thing should be. And you'll notice that the velocities only match for the actual feature down here, and these black dots are velocities that are way off, so they're things that are at very different distances in the galaxy. So let me show you, hopefully on the projector you'll be able to see. Can you see this? If you follow my laser pointer, you see this black line going all the way. And if you look at this in the far infrared, it's actually a little bit more continuous. Okay, so it gets broken up by H2 regions. I'm choosing to give Nessie kind of short shrift today because this is a 5-year-old result and I want to talk about the new stuff. Okay? But it's important to know that these things exist. Okay? So here is Jim Jackson at BU at the time was actually the person who discovered Nessie in the Spitzer database. And this thing here that says Nessie Classic, that's Jim's version of Nessie that was 80 parsecs long. And the paper that he wrote was about massive star formation in this. So these are regions, molecular clouds that have lots of massive star formation, but we're more interested in them for their larger structures. And so this, I think we called it, yes, Nessie extended. Okay, so nobody doubts that all of this structure is connected, and this is just an H2 region in the middle that breaks it up. Okay, and then this white line is alternatively called Nessie Crazy or Nessie Alyssa. Okay. And actually, the Herschel data that came after do show that this is all continuous. Okay? But anyway, so it's somewhere from 150 to like 500 parsecs long, depending on who you believe. Okay? But it's very long and very skinny. You can't see the transverse extent on here, which is why it's so difficult to see it on an image. But if you zoom in, it's a parsec or less.
White line data or a fit?
No, that's a fit. That's just a trace of the thing. No, that would be great, but no. And then here, just to show you where it is in the galaxy, so this is a cartoon model of the galaxy that we'll get back to later. The sun is not to scale on this cartoon, okay? But anyway, so that's the sun, and you're looking toward the center of the galaxy, so you have a sort of bright illumination, but slightly off the center of the galaxy, because otherwise you'd be blinded, you wouldn't be able to see it. And so we were very happy that when we found this, you know, here it goes right there. It's in the Scutum Centaurus arm. And so when we found it, we said, oh, good. You know, you should always find the one that's easiest to find first, right? So it's like right up close with a really bright background and in an arm that's perpendicular to our line of sight. So you realize it's very hard to find something like this if you look, say, here, because there's no perpendicular component of something that would be along that arm. Okay, so many people said, you know, are there more of these things? And so there are the numbers. I'm sorry, I should have put them on the previous slide, but 300 parsecs long and 1 parsec wide. And so, okay, so now remember those kind of numbers.
And just so before we went and looked for more of them, we did look for whether or not you could see these kinds of things in any of the simulations. And actually, the simulation I showed you before, the one from Rowan Smith, thankfully came out at roughly the same time that we did this work. And before that, so this is the simulation here, uses a repo, which many of you know can have a very high dynamic range and resolution by having a moving mesh. And so you see a top-down view here of a little, oh, sorry. I really think I have failed your IQ test. I'm sorry. But anyway, so you see a top-down view in the corner, and this is just a little section of a side-on view of one of the arms in that simulation. And you'll notice, OK, it's a crapshoot. Should I go forward or backward to get the image back? Let's go backwards.
Sorry, that's
Nope.
Sorry.
Sorry.
That is gas or molecular gas or what exactly are we looking at that?
I will answer that. The green that you see here is emission from dust in the mid-infrared, and the orange that you see in the simulation is simply a column density map. Okay, so this is only a comparison of plausibility of scales. This is not a detailed comparison. That's 3 papers later, which I'll get to in a minute. Okay, so this is just to say that if you looked in a simulation that, by the way, has no magnetic fields and no feedback, okay, and no self-gravity of the structures themselves, there's just a imposed spiral potential. So it's a very artificial simulation, but it's the only one that has enough resolution to look at this. Yeah.
No dust.
Sorry?
No dust.
No, so there's no radiative transfer of dust, although there is some assumption about the dust because this is the same simulation where the synthetic CO maps were made. So there's some sort of cooling assumptions that are made that imply some amount of dust. Yeah, okay. Right, so there are things that would be that small and that long in these simulations. So that was reassuring. Previous simulations, by the way, had a resolution of like 50 parsecs off the disk, so there was no way to see anything like this. Yeah?
Remind me what the circles mean.
The circles are positions where dense molecular gas was measured, so not CO, but denser molecular gas tracers, and so we know the velocity of the gas at those positions. And the comparison is of, if it's a white circle, the velocity is within 2.5 kilometers per second of the predicted orbital velocity for the galaxy at that distance. And I may not have said this, but this is at 3.1 kiloparsecs from the sun toward the center of the galaxy. And so the lines that you see here, the colored lines, are showing you the same rotation curve derived velocities, and so you can also just compare the color of the line to the color of the dot.
And the black dots?
The black dots are way off. So they're also measured, but they're at tens of kilometers per second off, so there's something somewhere else in the galaxy. So right, so it's good that the ones that line up with the dust structure are also the ones that are at the right velocity to be at this 3 kiloparsec distance. I've given whole hour-long talks about Nessie, and I'm sorry for trying to explain it in 5 minutes, but hopefully you'll believe me that there is at least one of these 300 parsec long 1 parsec clouds. And so just to give you a orientation, here's the sun and here's Nessie in this lovely cartoon, although Nessie's a little big in that drawing. But importantly, it's toward the inner part of the galaxy. Okay. And we would love to know how many more of these there are. But you might notice that it's a little hard geometrically to see these things as shadows if you don't have a relatively bright background. So it's very hard to see them in the outer galaxy. So most of the searches for Nessie-like objects have been toward the inner galaxy. So there's a little bit of an observational bias there. So after we published this paper, a number of groups started looking for these things in a variety of ways, in CO, in Herschel data, in optical extinction, in all kinds of things. And there were many claims of long filaments. And Catherine Zucker finally took it upon herself. These are her 4 recent papers that are relevant to this. I don't expect you to be able to read the titles or the details, but the slides are online. So if you actually want to read these papers, you can go click on these and see what they are. But the upshot of all of these papers is she went and found all of the claims in the literature of similar objects, reobserved them in the Herschel database, ran a new algorithm that she and another student, Hope Chen, developed to actually systematically identify their aspect ratios and their orientation, and then plotted a comparison, which you see here on the left, a cartoon comparison, I'll explain how it works in a second, of all of the things that have been observed that are at all Nessie-like. Okay? So she herself found another sample in the Spitzer database. This is what says Milky Way bones here. And the way this cartoon works is 0 is a galactic plane. This is real scale, height off the plane. So this is 50 parsecs, 100 parsecs. The XY orientation here, the X orientation means nothing, the X position. It's just laid down some pickup sticks so that you could see what this would look like as a distribution. And then the orientation and aspect ratio of these things is representative of what's actually observed. So you'll notice that the Nessie-like things are very long and skinny and very near the plane and very systematically oriented parallel to the plane, preferentially parallel. These things are detected in CO mostly by Thomas Henning's group in Heidelberg, and they are really kind of just big elongated molecular clouds. And you'll notice that they're wider and that they're farther from the plane and that they have slightly more random orientation, although you realize you can't have an orientation very perpendicular to the plane because you run out of CO in the plane, okay? Except for the Radcliffe Wave, which says you can get to about 150 parsecs. But anyway, so this is one distribution. And then there's some other claims where people have searched the Herschel database, and those things are kind of far out of the plane. And then there's these things that are a weird algorithm for finding molecular clouds, but interesting. So anyway, here's the sample observationally. And then over here, this is what happens if you do take Rowan-Smith simulation and do the best you can to synthetically observe what you would see from dust as observed by Herschel. Okay, so there's a whole procedure that's described in the 4th paper over here where that's done. And then these are objects that you would derive if you were observing that simulation from a vantage point like the sun, and what would their orientation and size be. And you'll notice they look kind of like these giant CO filaments, and there's nothing found that's actually as small and long and skinny as any of these filaments. So even the state-of-the-art simulations actually still can't find anything that's truly identifiable. In other words, your eye, when you looked at those orange pictures, you could see like stringy things. Maybe that was it. But algorithmically, we can't pick those out.
You just, so the synthetic ones were, so they're gas simulations where you then say what would the dust.
Exactly.
The dust would look like.
Exactly. There, yes, exactly.
With self-gravity and no star formation and no feedback.
That's right. So the next work that simulation, this comparison is still for those simulations that have no self-gravity, no feedback, and no magnetic fields.
What makes things thin in the first place? There's no self-gravity.
No, there's gravity in the simulation, but there's it starts with an imposed spiral potential. And so that's it. So there's self-gravity in that there's self-consistent gravity in the simulation, but there's no simulation of an isolated thing where you then follow it for longer and see what the gravity would do to it. I think the biggest problem with these things is that there's also no magnetic fields. And also, I don't know if it's evolved long enough to make sharp enough structures, and I think that the algorithm can't pick out the sharp structures well enough, because your eye sees things that are longer and skinnier. The equation of state in the simulation? It's nothing unusual. I don't know. There's not, the CO is calculated after the fact, so there's not some kind of self-consistent heating and cooling, as far as I know, in the simulation. It's possible. Yeah. That's right. That's right. So anyway, what's going on now is that Rowan-Smith, and I don't know whether anybody here is a collaborator on that, is working to include feedback on magnetic fields and a better treatment of gravity in these simulations, partially because you can't reproduce these structures. Okay. So that's where we leave the bones for now, that they exist, but that a full theoretical reproduction of them is not yet available.
To
Sure.
what extent are they as neutral? To what extent do they cross?
Yes, I didn't put that slide in. So in the simulation, oh, actually, I sort of did, because if you go back here, let me just go back. You see the blue and the red? So the image is too small to see, but basically the ones that say arm and then the ones that say interarm. So the ones that say arm would be, you know, in an arm, like along a circle, and the ones that say interarm are this kind of webby stuff between the arms. So is that what you were asking? Okay. Okay. I can show you the details of the red and blue highlighting on the simulation later, but I left that out. Okay. All right, so we noted that the bones were toward the inner galaxy, or in a position vaguely like that. And so now finally I want to talk about this wave-like structure. Okay? And importantly, it is toward the outer galaxy. So these two results, while they seem kind of contradictory, right? Because one says there's this thing going 150 parsecs out of the galaxy, and the other one says there's this thing lying less than a few parsecs from what appears to be the gravitational midplane of the galaxy. The only way that you can reconcile those two things, if they're both sort of generic, is that the bone-like things are toward the inner galaxy, and the wave thing that I'm going to show you is toward the outer galaxy, where the disk is a little bit thicker, but we didn't know that much thicker. Okay. So the infamous Radcliffe Wave. So I'm going to do something super dangerous and attempt live demo. And I have a movie in case it doesn't work. Okay. So I left this lovely, you heard that I also like to work on data visualization. And so somewhere here, I left running the glue software that we use to analyze all these data. And you probably can't read this list, but these are all sorts of different marked components. And there's one image, which actually I'll show you the output image first, but then I can show it to you in the context of the galaxy. So this is the interactive figure that is in the Nature submission. And you can click and see the top-down view, the side view. So these are the figures from the paper that you saw before as stills. And you can manipulate these things so that you can see what's going on.
So the coordinate system here is such that X runs...
The galactic center is to the right, to my right here. And then the sun is where the yellow thing is. And this is a straight top-down view of the galaxy in a Cartesian coordinate system. Okay? And so some important things to notice right away is Jim's question. So the other clouds are these light blue dots. Okay? So why aren't they in this structure? Good question. And the answer is, if you actually look at, I will show you now. If you look at an image like this, which is just all of the dust on its own, let me turn that. Okay, so we can manipulate this in 3D. So if I put this straight down, you see this big, long, dark thing that your eye picks out? Okay, so those are those red dots. And then what happens is you put down a rectangle over that region, and you start experimenting with where that rectangle would go and how good a fit you get to the data. And so I will show you here that if I turn on this best fit model, okay, so that's a damped sine wave fit to the wave-like points. And some of you know Josh Spiegel, who's an excellent graduate student we also work with, and he's a very, very skeptical statistician. And the extremely long description of the parameter optimization for this fit is in the paper, which again, I'm willing to privately share with any of you. But we managed to convince him that this wasn't cherry picking. But it is true that you kind of wonder what the other clouds are. And so let me just tell you that some of them are actually the Sagittarius arm. So if I turn that on again. Okay, so this stuff over here has to do with a different spiral arm of the galaxy. You might also wonder, where's Gould's belt? So how many people here have even heard of Gould's belt? Oh, wow. Very, very savvy bunch. Okay. So Gould's belt is this structure that's supposed to be made of young star-forming regions in the proximity of the sun, and maybe has something to do with the local bubble. And a lot of it was made out of Hipparcos data. And there have been some Gaia papers that still say that it exists. But it turns out it's not a very good fit. And it actually appears to be, let me turn off this other stuff, a projection effect. So I'll even turn off the fit. So if you look, oh, not that fit. We want that fit. Oops. This is the live demo danger part here. We want the fit to there. Okay. So if I turn this around, you see how this tilt of Gould's belt is kind of the tilt of that part of this wave fit? And so the thought is that the sort of left side of this was real, and the right side of it was wishful thinking plus a bunch of small molecular clouds that actually fit on that side. So I'm afraid that the paper pretty much says Gould's belt is dead. And by the way, Gould was a Harvard astronomer, so, you know, sorry. Anyway, all right, so no more Gould's belt, and here's this thing. And then what's really fun is if I go back to glue here, and I show you this. By the way, I can put the points on here. Okay, so here. So now you can see how those red points line up with the true 3D dust map. Okay, but the really fun thing is if you actually look here. So this is, for those of you who care about visualization and that kind of detail, this is a worldwide telescope inside of glue. Okay, so here I can have a cartoon model of the galaxy, which was made by Robert Hurt in consultation with lots of people who work on masers and H2 regions, and they put together their heads and made this sort of data-driven cartoon. And I will tell you that we were just plain astonished, okay, the first time we put these data, which of course had nothing to do with the making of this cartoon or with maser data that I'll come back to in a minute. And so we put, let me just turn off the fits, and then I have to say why the local arm fit is so bad. Okay, so we turned on these data in this cartoon. Let me turn off the masers too. And we were just shocked at how well, let me turn them off so you can see, they fit right in this dark lane, okay, that our cartooning genius Milky Way in their head friends had made. And so,
Put in Gould's belt.
no, they put in the clouds that were associated with Gould's belt, which is how you get that dark set of spots there. And then so you can even see, like if I turn this, you can kind of see how the sine wave goes above and below the plane of the Milky Way. And so originally, when we found all this, we called in our friend Mark Reed, who we sometimes collaborate with, but not on this paper. And I don't know if you know, but in the media, they have this expression called a red team, where you're going to publish some crazy story and you bring in the other reporters to tear your team's view apart. So we brought in Mark Reed and Tom Dame to say, please tell us what we did wrong. And at first, Mark thought, well, I don't like this because my fit, meaning his fit from masers, and I'll talk about how you use the masers in a minute. So the blue dots there are the masers. Actually, you can probably see this better without the galaxy on. So let me put this back like this. Turn off this fit. I'll turn on, there you go. So the blue dots are maser distances. And so just because I think some of you might be skeptical, I'm going to just skip and show you something. So hopefully you all know how trigonometric parallax works, and that this is considered the absolute, gold standard of astronomy, and that you can't make a mistake on the distance if you can measure trigonometric parallax. So this is the comparison, before I go any further, of the maser distances, the trigonometric parallax distances from Bessel with dust distances where there are shared lines of sight. And I don't know about you, but you don't see this kind of thing in astronomy very often, okay? Scary. Yeah, you were going to say something.
And the dust distances are from embedded.
They're from the technique that I'm going to finally explain in about 2 minutes, okay? But they're from a statistical analysis of what dust distribution would you need to explain the reddening distribution that you see, knowing the distances to many stars in 3D. That's the 2-sentence answer. Okay, so going back here, this is the fit to the local arm using trigonometric parallax maser distances. You'll notice that if I turn actually the Radcliffe wave off, okay, and the connections here, that it's not like a spectacularly good fit locally, okay? What it is they're trying to fit a log normal to the entire spiral arm, okay? And so locally, it's just not a very good fit. And so when we looked into this and when Mark saw that one-to-one plot between the maser distances and the dust distances, he said, whoa, okay, that is the spiral arm, okay? So one Milky Way expert surveyed agrees, and Tom Dame too, that this is the spiral arm. Okay, so the spiral arm doesn't go like that. The spiral arm is actually straight. and has this sinusoidal curve in it. So if we go back to, where were we, glue, okay, that's what we're talking about, okay, this red thing. Okay, so now I wanted to talk about how this actually works, because many people want to know. Before I do that, you also probably want to know this, which is the fitted parameters from that black line that I showed you a minute ago. So here's the length, 2.7. The scatter is sort of the thickness, so that's about 60 parsecs. The amplitude says 160, and the mass, the lower limit is 3 million solar masses. And that's because the reason it's a lower limit is it's very hard to separate in the dust, which is the reliable way to measure mass, the background from the actual feature. And so it's a lower limit. Okay, so how do you actually do this? The answer is a 10-year effort by Doug Finkbeiner's group and his many smart students and postdocs, and then the advent of Gaia DR2. But I will give you an answer, hopefully, that is more understandable than that. So here's some stuff. Okay, we're not going to say whether it's dust or gas. For the purposes right now, we'll just assume this is interstellar matter and that it's dust mixed with gas. And we're not going to talk about the differences between dust and gas for the moment. Okay? And so there's some 3D box around that stuff. Then you have Gaia, which I think you know uses the same kind of trigonometric parallax as the masers to go ahead and find amazingly accurate distances to these stars. Okay. So now we all know the way imaging works. You know, the light from some star makes it to some imaging plane. And if you have a very boring set of stars at different distances that are all exactly the same color, you know, you would get an image of lots of stars of the same color. By the way, also not to scale. Sure you're good with that, right? Okay. So anyway, there's your image, right? But now, let's say that you had that same distribution of stars, but you also have that distribution of dust. And now also you have to imagine you have very big computers and very smart people, okay? Because what I'm going to say next sounds kind of amazing. Okay? Why am I showing a picture of a sunset? Because I'm just going to remind you that what stuff in an atmosphere or stuff in interstellar space does to light as it passes through that stuff is it changes the color, okay? It makes it red. And so we can convert from reddening to extinction, although exactly how you do that is also at issue, and that's a whole conversation we can have with Bruce. But let's say that we understand how to convert from the reddening caused by this stuff to extinction. Then what you do is you look at how the color of each star changes along each line of sight, and then you remember the part about the really big computer? So now imagine that you have 100 million stars, not that many stars, and they're distributed in 3D, and you know something about their spectral type from a color distribution, from models of the distribution of colors of stars, because you have a very broadband spectrum, let's call it an SED. So there's many wavelength observations of the star to estimate the spectral type of the star. So you know its intrinsic color. Then you have a 3D distance, okay? And then you have an optimization statistical problem where you say what three-dimensional distribution of stuff would give you this two-dimensional color image that you see, okay? And so that's the lots of computers and 10 years of people, okay? And all I'm going to say is that you can infer the distance of matter along any so-called sight line from this technique. And this is just a sample of hundreds of figures like this in all of these papers that show you what happens when you look. So this is distance modulus, but you can just think of it as distance. And so you start out here, and eventually you get to a point where there's a huge amount of extinction along a particular sight line, and you say, okay, this blob of stuff must be at this distance. Okay? So you do that for many, many adjacent sight lines. And what was true until 2019, until just recently, was that was done uncorrelated, pixel by pixel. Okay? So the latest work that Greg Green has done, this map I showed you before, actually takes into account what should be correlation of neighboring pixels so that you don't get weird jumps. And that makes for a slightly smoother extinction map. And so it's those data that I've been showing you and that have been used in this work. Okay. So now the questions for theory are what the heck is causing either of these things. And so I think they have something to do, certainly the bones, with the overall gravitational potential of the galaxy. The thing on the right, most people we've talked to think it has to do something with some kind of collision, that something, dropped in from the halo, from who knows where. And Jerry Oestreicher, who I was talking about this with yesterday, pointed out that whatever that thing is probably shouldn't have too many stars, or that we would see a leftover pattern in the stars. It's also very strange that what we do know about the radial velocity of the gas looks like the gas associated with the Radcliffe wave is at a normal rotational velocity for the galaxy. So whatever it was that was coming in wasn't at some bizarrely large transverse velocity, if it was even a collision. And I just want to tell you a very funny story, which is that this guy, who some of you may know, is Gus Bean, who's a first-year graduate student in our department. And I was at a reception for him last week where we were honoring John Huckra and showing the tour that Jim appears in, Worldwide Telescope tour, in a museum. And he pulled out his phone because I was telling him about this Radcliffe Wave thing. And he said, oh, look, I just worked on this paper that has these oscillations in the Milky Way disk, which came out like a month ago. Those oscillations are caused, that's this lower panel here, by the collision with the Sagittarius. And they're too big. The wavelength is too long. But the amplitude is kind of right. And so I don't know if anything hit the Milky Way. But something odd happened at the position of the Radcliffe Wave. So I don't need to show you this again, but we'll just flash through it. And what I wanted to say is that the masers require there to be masers on this. So the maser is an uncommon phenomenon, whereas dust is a very common phenomenon. So this dust mapping, dust distance mapping, is extraordinarily useful because you can use it anywhere. Okay? So the last thing I wanted to say is just, what about 4D? What if you could combine the spectral line cubes with the dust distances? And the short answer to that is it works very well. And there's been this one experiment using that Perseus molecular cloud that I mentioned at the beginning. And what Catherine Zucker again did was to find the distances to each one of these sort of blobs in that cloud using the 3D dust, and then also have the gas. And the absolutely bizarre thing is that it turns out that in that one cloud, if you look at this plot down here, which is distance versus velocity, you actually get a correlation. So there's this weird, it's not caused by expansion, okay, but there's this weird Hubble-like velocity, Hubble law-like velocity distance correlation in the cloud. So that movie I showed you actually sort of is a 3D real movie. But you can,
One blob, or we're looking
sorry?
at each dot there is a different blob there?
Yes, each dot corresponds to the color of each section here. And then there's velocity slices that are made, and there's a distance assigned to each velocity slice.
So is the velocity, the feature is not perfectly azimuthal, so it has some range of extent.
Oh yeah,
So
that's true.
Is the velocity seen there consistent with what one would expect just from the York constants and the radial extent?
Oh, this is a very small cloud. So this particular cloud is like 20 or 30 parsecs long. And so there's not a lot of gravitational shear. Anyway, so the goal, right, is to knit together the information from the dust, the gas, and the stars. So we sort of felt like we were teasing out a story with the Radcliffe Wave, but really what we want to do is knit it all back together. I am not going to explain this to you, but if you want to know what we're doing, that's what we're doing, okay? So there's a lot of people involved, there's a lot of data, and there are a lot of very clever statistical advances that needed to be made and mostly have been made, including a complete reanalysis of how you do the stellar colors that will also improve the 3D dust maps. And that's being done by Josh Spiegel, who's working on this Brutus algorithm that's highlighted there. So, our goal is a knitted version of a galaxy. And I just wanted to conclude by explaining why this is just possible now. And the answer is that these wonderful maser VLBI distances have been available for a really long time. The kind of visualization tools that I showed you, like Worldwide Telescope and GLUE, which were really key to figuring out what was going on, are much more recent. And the most recent thing is Gaia DR2, which allowed for these distances to get so much better. So that's pretty much what I wanted to tell you. Thanks.